solution when this is all done is going to be what? Positive. Very good. So when I start seeing values like this with the monomials, I know that it's going to wind up becoming positive when I multiply the two negatives together. It doesn't matter if it's numerator or denominator. That doesn't matter whatsoever. But I know in the long run, when this all gets multiplied out, it'll be positive. Now the other thing is, inside my parentheses, if you think about your order of operations, you'll notice you have some negative exponents right off the bat. So those negative exponents, I'm going to move up. Okay? I'm going to move them up right off the bat. So I know that I'm going to have 2y z x, z x to the fourth, x to the third, y to the first, z squared, all over 2x to the fourth, y to the third, z squared, to the negative 1. With me so far? Okay. Order of operations, thinking about PEMDAS. If I'm looking at the interior there, then I start simplifying some stuff right off the bat. That's where I would start simplifying. What's 2 divided by 2? 1. So I know that the 2's will drop. I have an x to the fourth, an x to the fourth, a y to the third. Well, let's just do this one at a time. So let's write them out. We have x to the seventh. Took care of those. Y to the second. Z to the third. Denominator 4, 3, 2, and it's all the negative 1. Are we okay up to this point? Granted, I know you could probably shortcut this and do some other stuff at the same time, but just to make sure that we all see where this is heading, that's why I usually take my own sweet time as I get into this. Plus, when we get to fractional exponents, you're going to want to slow down. Play war. 7 or 4, who wins? 7. So your numerator becomes x to the third. We'll leave that there for right now. 2 or 3, who wins? The 3, so it goes y to the first denominator. And then lastly, a 3 and a 2, who wins? The 3, so the z stays up top. Now that negative 1, I'm left with, I've done everything on the inside of the parentheses, taking care of all the exponent rules and everything in there. The negative 1 then is like remember how we did that power to power? Mm-hmm. So basically that negative 1 has to be distributed to every exponent within the parentheses. So you wind up with 3, or x to the negative third, z to the negative 1, and y to the negative 1, which means everything's unhappy where it's at. So everything needs to get flipped. You get y over x cubed z. Does that make more sense? Seriously, when you do these things, it's much easier sometimes to go the long way by taking your sweet time to get there than it is to try to distribute that exponent and knock it all out at once. You're less likely to make a mistake if you just go a little bit slower. Okay, that's the only reason why I do it that way. Yes, sir. I'm sorry, I couldn't hear you. What's the number out in front that you don't see? 1. Okay, so what's negative 1 divided by negative 2? What's a negative divided by a negative? So what's negative 1 divided by negative 2? That's why I got rid of it. Count the negatives of your coefficients, and if it's an odd number, it stays negative. If it's an even number, it becomes positive. Works every time. Squirrel. There's a couple of good songs. I'll give you that. Yes, there's a couple of good ones, and then what's his name? Roy Hobson. Roy Hobson. He had a really cool solo album. I forgot the name of it. Like "Who's the Stranger" or something like that. But yeah, there's a couple of good tunes. Random thoughts. Xander, what do you got? Welcome. Oh, you want it all the way down? You knew I was going to do that. I mean, come on. All right, make sure your name's on that. We'll send that up, and then let's talk about 6-3. 6-3 is pretty quick. We'll be able to go 6-3 and start a little bit of 6-4 as well. Yes, ma'am. Yeah, it was on the calendar. You saw it. You don't have to read it. You can look at it and write it down. What do you want? It's in the yellow folder because after all that walked away, I don't want to yell at you. You're welcome. You could have looked at it online too. Yeah. 30%, 97. Alright, so 6-3. Adding, subtracting, multiplying polynomials. There's a couple little quick things before you get too far and write anything down. Guys, come on. There's a couple of quick things I want to make sure you guys see before you get too far and write anything down. When you look at this first term, what's the degree of that polynomial? It's a third degree. Now, it's a third degree polynomial, which means how many parts are in its, terms are in it, excuse me. It could have up to 4 possible terms. If it was shown with just 2 terms, that meant you had to have a couple of placeholders. What did I call that were placeholders again? A 0, but yeah, if you had like x to the third, no x squared, and x and a constant, then you'd have to have like a 0x squared thrown in there. Something to hold place value for you. Okay? Now, this is where that idea of having that place value holder is going to come into play a lot. Now, we're going to add and subtract these things. Textbooks generally always write, put away your cell phone. Textbooks generally always write stuff out horizontally. And I don't like horizontal math. There's a time and a place for certain things. Addition is not one of those, or subtraction is not one of those I like to show horizontal math for, because I'd rather do this. 3x cubed. Watch that shift on that mother function. Actually, I'm sorry. It's supposed to be holy shift. Look at the asymptote on that mother function. You have to be very careful when you say that. The fact that you're quoting your text, your book, that you think that's funny. This is like great. Anyway, hey, what did I just do? Spread it out. Now, when I put in the other one, I rewrote it underneath everything. Because I have to add these guys together. It's much easier to do stuff vertically. It's not so much as important with addition, but with subtraction, knowing your guys' track record with the distributive property, it's much nicer to rewrite stuff vertically so that way you know that you have to subtract each and every piece. Addition, it's usually not a big deal, but it's easy to show why this works. So what's 3 plus 1? 4. What's 2 plus negative 10? Negative 1 plus 0. Negative 1. And negative 7 plus 8. 1. Basically, addition and subtraction is a whole lot of combined like terms. That's really all it is. addition more so than subtraction. When we have subtraction of polynomials, is where you have to be very careful about your signs. That's why I always write these things vertically, because you line it up underneath each one individual part, you'd be less likely to mess up. So anytime you see this horizontal stuff, automatically rewrite it vertically. Just space it out a little bit between each piece so you can draw that you've got X number of subtraction or addition. For example, here's two trinomials, 5x squared plus x minus 7, minus the quantity, 3x squared minus 6x minus 1. So when I write this down, as I read this problem, I'm not going to write it horizontally. I'm going to automatically write it as 5x squared plus x minus 7. And I just space it out ever so much. And then I rewrite underneath it. 3x squared minus 6x minus 1. And I have 3 subtraction values. That's why I do that. It spaces it out, and it forces you to distribute the negative to each individual part. 9 times out of 10, that's what you guys pick to do. If you want, I don't like to do two things at once. It's just me. I'm lucky I'm chewing gum and walking right now. I'm not falling over. So. Twice. I got her on the holy acetone. They're getting you walking and chewing gum. This is funny. What's 5 minus 3? 1 minus negative 6. Negative 7 minus negative 1. I know it seems remedial to do it this way. This is how we teach Algebra 1 students. But I'm telling you, I know how you guys make mistakes. And usually it's making mistakes with distributed property. Okay? It's a very simple way to alleviate making a dumb mistake. Okay? Why are you going cross-eyed on me? Is it hurting? One minus negative 6. Whenever we do same change, opposite. That's why I do it this way, because I said it, I didn't mark it. That's adding, subtracting. Now, the other thing that we'll do is multiplying. Now, we talked about this in first hour. When you do your multiplication stuff, this is one of those that it kind of makes sense to stay horizontal. Because when you did your multiplying binomial times binomial, we would FOIL stuff. In this case, I have a binomial and a trinomial. There is no foiling of that, if you will. Exactly. You have to do that stuff over and over again, which is called the... And what I would do, if I were you, is I'm always going to do my arrows for the first 3 or however many you have to do. Distribute out. Distribute and write it down. X times 3x squared is 3x cubed. X times negative 2x is negative 2x squared. X times negative 4 is negative 4x. I get my first 3 pieces. And then I do the same thing with my arrows, but instead of being on the top, I'm going to draw my arrows on the bottom. To remind myself to hit all 3 of those. Okay. Negative 3 times the 3x squared gets you negative 3, negative 2x, and negative 3 and negative 4. I almost forgot the x. And then lastly it's combined like terms. Always put your answers into a descending order. And another thing that I always like to do with these is I always like to mark off the ones that I've worked with and cross them off so I don't double count something. Because not always is it just going to be 4 terms. It might be 7. So you have to be careful how many you wind up with. I underlined the first one. We have 3x cubed. Cross it off because I took care of it. Underline all the next ones. -2, -9 gives me -11. Cross them off so I don't double count. -4x and 6x, 2x, and then I'm left with then. Good. I hope. There's not a lot. There's reasons why we have to do this now because, and I'll show you where this is heading towards here in a second. I don't know. So let's see. That's correct, but we're dealing with terms here. So. Real fast, when I'm looking at this, what's 2 times 3 times 4? 24. What's 3 times 4 times 2? What is 4 times 2 times 3? 24. What's 4 times 3 times 2? Does the order in which you multiply things together matter? No. So what I would do here, when I see a bunch of binomials, 2-term pieces, what I would do is I would FOIL the second parts, the second and third ones, if you will. Because then it looks like the problem you did a minute ago. See what I'm saying? Yeah, FOIL it out. Do that first. Because your mind works better distributive property-wise going from left to right. So if you can combine stuff that's all on the right to begin with, and then distribute through that, you'll be better off. That's normally where you guys will make a dumb mistake. Always take care of the back half first. So then you would just distribute that one out, just like the one we did a second ago. X cubed. Nice. You get all of that? It is. But then you combine your like terms, you should only have 4 terms left over. X cubed. Oh, I'm sorry. Thank you. Sorry about that. I didn't realize I did that. I think it was in my head. It was going, oh, I got to do something. So what people were asking first hour was, okay, this is fine and dandy, but why are we worried about this now? Well, what I want you to think of is this. Last week I showed you guys, we talked about what was 16 divided by, not 16, sorry, 18 divided by 3. It was 6. You put the 6 here, you multiplied through, you had a remainder of 0. We knew then that 3 was a factor. 3 was a term of 18. Okay? This was a whole number that went into it. If I did 5, 18 divided by 5, 3 multiplied through, drop to 0, you wound up with a 0.6. It still went into it, but it didn't go into it as in full integer value. You had leftover. You had a remainder to it. So was 5 a factor of 18? No. Okay. Same idea is going to happen here when we get into, oops, this guy. So in this one here, this polynomial was created by the terms x minus 4, x minus 2, x minus 5. Was that correct? Okay. So that means that the factors of that polynomial are x minus 4, x minus 2, x minus 5. What are the zeros of that polynomial? 4, 2, and 5. So this has zeros at 2, 4, bless you, and 5. Now, one of the other quick things you guys were working with on Thursday, Friday, and a little bit yesterday was this thing called synthetic substitution. Remember that? It's nice, isn't it? So if I take my coefficients here, what are my coefficients of that polynomial to start with? 1, negative 11, okay? Now, what's going to happen here is that we're going to have to learn ways in which that we can factor higher degree polynomials. Well, if something is factorable, that means we have to figure out one of their terms. Terms generate zeros. So we know that if 2 is a 0, because it has a term of x minus 1. So if I use 2 here, watch what happens. Our first step was always to drop the 1, whatever the first coefficient was. We'd multiply and add, multiply, add, multiply, and add. Do I have a remainder? No. It went in there cleanly. As I divided that, or divided by my 0 in this case, 0, I'm just using, because we knew that 2 was one of the zeros from the original part of the problem. Remember they gave us these 3 terms multiplied generated that polynomial. I know that 2 is a 0, 4 is a 0, 5 is a 0, so I'm just going off of that. Okay. Now, when you divide stuff out, you're basically figuring out parts of it. So if 2 was the 0, that meant we took the term x minus 2 out of that polynomial. So if you start with a third degree polynomial, you took out something that had 1 degree, how many degrees are left? 2. That means you're left with x squared minus 9x plus 20. What times what's 20? You add together to get negative 9. That's why zeros in terms are so important. We're going to be doing this for quite some time. But the idea is understanding the relationship that's created between terms and zeros. Okay? Because if we're able to figure out if we're able to find, remember you guys were joking the other day about search party for zeros, we're able to search for zeros. If we can find zeros, we can factor anything. All right, that's the idea. Okay. And that's where this comes from. This is where this is going. Okay? That's where this is going. Let's see what's the other one. There are a couple of special patterns. It's not that important, to be honest with you. There's no reason, there's no rhyme or reason that we have to make sure that we that we write all these out or memorize all these things through. What I just want you guys to remember is that don't kill a puppy. When you see junk squared, make sure you rewrite it as junk times junk. Make sure you rewrite that and you FOIL it. Okay. It's the only reason. Nice. The only reason that I say that is because at least two of you guys on a daily basis will rewrite this as 81y squared plus x to the 4th. At least two of you will do that every single time. Whenever you see, it's good money to take that back. I'm telling you, whenever you have junk squared, write it out. Write it out. Okay? Yes, ma'am. What do you mean? Oh, if it's like 9y x squared? Yes, because then it's a monomial. Then you're just monomial times monomial. So when you FOIL this out, you get your 81 minus 18y x squared plus x to the 4th. You gotta FOIL it out. You get minus 9yx squared minus 9yx squared gives me 18yx squared. When you're adding these things together, you don't have to worry about your exponents. Same thing goes for with the anytime you have junk cubed, just write it out 3 times. Okay? You don't need to follow the special patterns. It's not that end of the world. If you have something like that, again, write it out 3 times. Normally no more than 4 because it just becomes stupid. Okay. So if you rewrite this through, again, take care of the second 2 and then distribute it in the first piece. It's a cleaner way of doing it. All right, it's a cleaner way of doing it. Remember, when you have junk times junk and you're FOILing it through, all you have to do is square the first one, a squared, b squared, multiply the 2 together and double it, and square the last term. Those are your special patterns for that. Or write it out. Yes, ma'am. AB quantity squared. Because I'm multiplying AB times AB. AB times AB is A times A times B times B. That's right, A squared. Okay. And then you FOIL out the last bit again. It gets messy when you have multiple variables. Bless you. Here's your first set. 2a squared, b squared. It's not that the mathing here is difficult. It's just making sure that you take care of your exponent parts correctly. And then you just rewrite. So if you start with the cube, go to the next. 4a squared b squared plus 2a squared b squared is 6a squared b squared. 4AB, 8AB, 12AB, and an A. Again, it's not that the math here is tough. It's just making sure you keep it clean. I'm not worried. I just couldn't remember if I had the one right after that. It was so long ago. You guys actually got a pretty decent chunk to start with. You guys somehow got ahead of the other guys by a couple of questions. PDF is posted. By all means, go ahead and screenshot that now so that way you don't lose your internet later on. There's a textbook up here if you want to take a picture of it of yourself. But to be honest with you, there's no reason why this shouldn't take you more than 10, 15 minutes. Okay. Tomorrow we will start with the factoring stuff. This is kind of like a weird chapter where the first half with the adding, subtracting, multiplying, exponent rules, some detailed behavior. It's just really setting us up to be able to get into why algebras. And it kind of all starts off tomorrow with the whole factoring thing of the upper degree stuff. And what happens when we go into the factoring of the higher degree things, there's going to be multiple ways to do something. Whether or not it's a trinomial, difference of squares, really rude. Because in a minute you're going to say, what did you say? Whether or not it's difference of squares, sum of squares, which you could factor, trinomial stuff, four-term stuff. Each one of them has their own little pathways to do so. And as we get into them tomorrow, that's where it becomes really important to be able to understand what the problem's starting off with. We'll start talking about the factoring, finding all the zeros, and then we'll start looking back at where the tails are going via the zeros. Because if you go back to what was the one we had zeros at a minute ago? It was 2, 4, and 5. And I think the first term was a positive x cubed, right? Is that right? So where are your tails going? There's a positive x cubed, so down up. So that meant that our tails were going this way, so it has to come up to here, here, here. Oop, man, I messed that up. Now, where that crosses the y-axis, well, we're not quite sure on that one. The intercept, the constant value. How high and how low the max mins go, something we don't need to worry, but we know that the general picture of that graph should have looked like that. That's the idea as we get along into this. We'll be able to figure out more and more information. And again, it's the idea of why algebras. Why is that? For every value of the degree, there exists the value of the zero amongst the complex plane. So if you have a fourth degree polynomial, how many zeros should you have? 4. If you have a seventh degree polynomial, how many zeros should you have? 7. If you have a seventh degree polynomial, how many changes in direction should you have? Remember that one? It's one less, 6, and so on. That's where all of this gets into being able to draw that through. Yeah, could have had a V8. But are you changing as you go to here? Okay. 3 turns, 2 directions. All right. All right. All right. All right. Just keep your shoes on. We don't. I hopefully don't have to do like a 20th degree polynomial. You could. You guys show up for some test or something. I was working. You guys are all flip flops. Yeah. You guys like, wait, I'm counting out my toes.